The paper of the day is Robust Query Processing through Progressive Optimization. Traditional query optimizers choose an execution plan for a query by using estimates of current database statistics. However, these estimates can be inaccurate, leading to an overly expensive query plans being chosen and executed. This paper presents a progressive query optimization, allowing query execution to detect and recover from estimation errors during processing. During each execution step, progressive query optimization, aka POP, detects differences between cardinality of the currently processed tuple and compares that to the estimated cardinality that was used to define the original execution plan. If those cardinalities differ enough, POP will re-optimize the query using dated estimates of cardinality. Any materialized views already computed can be reused during the execution step. POP works by inserting checkpoints into query execution plan. Each checkpoint acts as an assertion that the planned estimates agree with the actual values seen during execution. The checkpoints are inserted between producers and consumers, which are stages of concurrently executing query. The checkpoints monitor the number of rows flowing through the producer and consumers and can suspend every execution if the number of rows it sees are widely different than the number of rows estimated, signaling an opportunity for re-optimization. The checkpoints are implemented as check relational operators within the currently executing relational query. The check operators have no relation semantics. Each check has a cardinality range defining the lower and upper bounds of cardinality estimation. If the observed cardinality during execution is within this range, the check succeeds and the query processing continues normally. If the observed cardinality is outside the range, the check fails and the query is terminated and re-optimized for re-execution. Any intermediate results are buffered and made available for the subsequent query execution. POP can be inserted into an existing query planner by adding the logic for check operator to the architecture. This implies adding logic that captures cardinality estimations for the check operator, that is, inserting check operators at appropriate points within an execution plan and adding the compiler and runtime facilities to generate and execute check operators. To reuse intermediate results, require adding logic to buffer and exploits the result if a check operator fails. Re-optimizing and re-executing a query can result in a significant performance hit. You only want to re-optimize if you are sure the plan will improve. With POP, the determination of the cardinality range for a check operator largely determines the effectiveness of query optimization. These ranges are computed by analyzing the different query plans that are considered while the optimizer prunes and enumerates possible execution strategies. POP uses numerical methods to approximate the validity range given the estimated ranges of several alternative plans. To exploit intermediate results of an execution, whenever a check operator fails, the end results are stored in a temporary materialized view. During re-optimization, these materialized views with their cardinalities will be available to the query optimizer during query planning. The paper shows POP can drastically reduce the execution time of a worst-case queries. However, in their findings, 22 queries receiving an improvement via POP, 17 queries actually experience a degradation. The author suggests that their check operator may lead to an over-eager re-optimizations, leading to queries that are re-executed with little benefit. Architecture of a POP. Extending a DBMS with POP capabilities involves the following steps: adding logic to the plan generator of the query optimizer to determine the check range by determining the cardinality range for each of the given operator is optimal in the current plan. Adding logic to the post-POP pass of the optimizer for deciding the most judicious locations for checks. Adding code generator logic for translating check into executable code. Adding logic to the runtime system for interpreting check. Adding logic to exploit intermediate results when check fails so that work done already can be reused during de-optimization. Contribution. The main contributions of this paper are: first, the concept and various flavors of the check operator, a novel method for determining validity ranges for QEPs, that is query execution plans, and a rigorous performance analysis of a prototype of POP. They explore alternative checkpointing schemes that impose different levels of overhead and investigate the trade-off in placing check at different places in the query execution plans. Paper also introduces check operators that permit re-optimization of pipeline plans without erroneously returning duplicate rows, a consideration implicitly ignored by prior re-optimization schemes in the literature.